In this session, you will learn how to backtest and update your pairs model. You will construct a static pairs model and identify the steps to backtest it. You will also learn about a method to dynamically update your pair choice and backtest it. You will learn how backtesting helps you to select an optimal pair. In the previous session, we discussed how to create a trade blotter. When you execute a trade, you keep track of the pair, direction, entry time and level, exit time and level, and category. You will produce an array of historical trades known as paper trades. You should assume small trading sizes because we are not using the bid size and offer size in our model. In previous lessons, you also learned about the basics of backtesting. I encourage you to review those materials if you need to. We will pick up where we left off with backtesting. You could backtest on static pairs or dynamically updated pairs. First, let's talk about static pair backtests. For example, we identified KLAC and ADSK. You could backtest using this pair statically for several months of data. The direction is determined by the relative performance of the stocks. The main advantage of running these backtests is simplicity. This will be your easiest test both to run and to assess. Similarly, you can run other static pairs. When you compare how good a pair is, the members remain fixed. Therefore, it will be easy to interpret and rank the results. Your optimal pair could be a weighted average of the following criteria. First, you seek to minimize the distance between the two stock loadings in component 1. You seek to minimize the distance between the absolute value of the two stock loadings in component 2. You will choose two stocks whose loadings must have opposite signs in component 2. Now you will look at a potential method to update and change your pair policies. You could dynamically update the principal components. In doing so, you will create new loadings. Recall that you base the pair selection on the principal component loadings. Your rule could be formalized to update the principal components with the last 12 months of data. Then you search for an optimal pair. Rerunning the principal components means that you would no longer stick with static pairs. Instead, by updating the data, you update the loadings. New loadings could facilitate the selection of new pairs. Of course, update frequency and choice of optimization criteria are key. Should these be part of the backtest? It will be difficult. You decide how often to update the loadings using your experience and the feasibility of computation in guiding your selection. Now we will talk about optimizing the parameters of your model based on 4 key performance metrics. Let's illustrate the backtest of a static example. When you run the data, recall that you are varying 3 parameters: entry signal, profit taking level, stop loss. As before, we will assume there are no timeouts. For each combination of these parameters, which is a model, you will want to expose the model to a history of prices. Suppose you have 50 different entry signals, 50 different profit-taking levels, and 50 different stop losses. In total, you have 125,000 combinations of parameters. You can clearly see the need to have efficient software. You write code that quickly produces a trade blotter. You also need to have code that quickly summarizes each trade blotter with your key metrics. You take the existing history of stock prices, as we discussed. You divide this into 2 unequal parts. Suppose you use 2/3 of the history for training and you use the remaining 1/3 of the history for testing. We'll call the first part the training data. We'll call the second part testing data. Now you begin backtesting. You take your first set of parameter combinations. You apply them to the training data. This produces a trade blotter. From previous sessions, you learned how to process a trade blotter. The trade blotter gets summarized by key metrics: total win, average win, percent win, expected loss, volatility, and steadiness of returns. Assume that you will use static pairs. You define an optimal criterion. You may choose the highest Sharpe ratio. This measures the total win per unit of volatility. Based on your 125,000 models, you select the top 50%. Now you proceed to testing. You want to see how well these models do on unseen data. This addresses the problem of overfitting. Overfitting means that you modeled patterns in the data you've seen, but you did not generalize the model to work well on data it hasn't seen. One of the best ways to avoid overfitting is to have some data that is held back when you are training the model. Then you present what you think are optimal parameters. Note that you take the top half of models from the training set. You will see how these perform in the testing set. Using the testing data, you produce a second trade blotter. You can select the same criteria such as the Sharpe ratio. You repeat this for all of the models you chose to test after the training round. So you now have over 60,000 models to compare. For each model, you have a training metric and a testing metric. You decide to pick the model that has the best overall performance. Suppose you use a criterion that weights 33% to your training metric and 67% to your testing metric. You get to choose the specific formula for selecting the optimal model. You select those weightings based on your experience with model performance in paper or live trading. In the next section, we will discuss how you can improve your model.